Okay, we will continue talking about energy today. I know the schedule says we're going to do fluids. Fluids is going to get a little shortened because energy is going to be a lot more important to us when we get to chemistry and geology than fluids will be. So let's get right into it. And I'm not going to do the root clap questions today. I'm just going to ask you to blurt stuff out today. A job can be done slowly or quickly. We had this question last class period. Both may require the same amount of work, but different amount of. What is it that's different if it's the same amount of work?
Momentum. Energy.
No. Power.
Wow.
So remember the definitions of all of these things. Energy is the ability to do work. And it has two types, potential and kinetic.
This is science, right? We're in science?
Yeah. Momentum has that symbol P, it's MV, it's a vector. Power is a capital P. How lovely is that? Lowercase p is momentum, capital P is power. So capitalization matters. And power is the rate at which work is done or the rate at which energy is converted. So you can write it either way. So that's why that was the correct answer, because if you're doing the same amount of work or the same amount of energy, it has work there in the question, but it's a different amount of time, then you have different powers. You remember my example with my brother Ron versus me having to go out and get things ready for Dad to plant or hoe the weeds or something. Finally, impulse. Impulse came from Newton's second law, solved in the form that net force multiplied by change in time is equal to the change in momentum. And this side here, we called the impulse. And of course, you remember we talked about things like why we have airbags in our car, how seat belts and shoulder restraints make them safer. Okay, so that's a review of what we did in class on Wednesday. Then on Thursday, we had lab. What did we learn in lab on Thursday?
Elastic and inelastic equations.
Okay, we learned about elastic and inelastic collisions. In theory, we would have completely elastic collisions and perfectly inelastic collisions. Ours weren't perfect, were they? Because our table, we didn't have all C's in one column or all NC's in one column. That's because experimental results don't always come out perfectly. There's lots of things that can go wrong, like we had friction, something we have to deal with. There's the possibility of somebody straying too close to the track and their body interfering with the measurements. There's lots of things that can go wrong in experiments. So you saw that it wasn't perfect, but you should have seen trends. So in those collisions, what was the difference between an elastic and an inelastic collision?
Inelastic bounced and elastic did not. Or am I backwards?
Backward.
Yeah.
That was the difference, though.
Conserved kinetic energy.
Elastic should have conserved kinetic energy from before to after. But as you saw, it wasn't in the middle. It dropped in the middle because energy was converted from kinetic into, in this case, magnetic potential energy, but then returned. That's what potential energy does. Potential energy will return energy to you. So we have gravitational potential energy that we're going to talk about some more today. We have springs. Springs will store energy and give it back. Rubber bands, clearly, you take a rubber band, you hold it against your forehead, you pull it out and let go, it will definitely snap back. And so you did work by stretching it, and it returned that energy by snapping back and banging you in the forehead. So we're going to pick up from there. So one thing about potential energy that's really a cool thing, it doesn't matter how you get there for the potential energy. If you have a bowling ball at the top of the stairs It doesn't matter if you brought the bowling ball up the elevator and put it there, or if you carried it up the steps. The fact that it's there says it has a certain amount of potential energy. That is, if you let it go, it can fall down the stairs and pick up speed, and if it picks up speed, then it's converted it from potential to kinetic, and then hit something and do work on that thing and damage it. So that's what this picture is trying to illustrate. It doesn't matter how you get the ball to an elevation of 3 meters. You could lift it straight up, you could roll it up an incline, or you could go upstairs. Ball traveled different distances in those cases, but it's only the elevation that matters. So, potential energy examples. I talked about a stretched rubber band, a drawn bow. As if we were into bows and arrows, you pull that string back. Where do you think energy is stored in a bow and arrow?
In the bow?
It's in the bow. When I was a kid, I always thought it was in the string. I wanted to get a really stretchy string because I thought that's where the energy was stored. Of course, we made our bows and arrows using pretty lame tree branches, so they didn't have much energy no matter what you did. But the bow is flexing. The bow is acting like a spring. And so you deform it and it will come back. Now, we have the words elastic and inelastic. The word elastic actually fundamentally means that if you deform it, it will come back to the way it was. So here's a spring. What that's saying is if I have this spring and I hang a mass from it, it'll stretch. That wasn't much mass, so it didn't stretch much. Let's put a heavier mass on here. It'll stretch more, but if I take the mass off, it comes back to where it was. It's not permanently deformed. In that case, it would give me back my energy. Whereas if I permanently deformed it, if it won't come back, then it's not going to give me back all the energy. Jessica.
This is a side note, and I'm just telling you because I'm going to forget for the 100th time, but in Moodle, the percentages are off, so I mean, at least us have Fs, even though we should have A's.
Yeah.
I'll check that. I thought I had it all set up. Yes. I want your grade to, I want you to know where you stand and not be like, oh. So I'll look into
I keep
that.
forgetting
Thank you
to
very
tell
much
you
for
for like
letting me
a
know.
week now.
I will look into it because I thought I had it all set up and I just put scores in and I'm like, yeah, they're. It's important that
Yeah,
you know
because a
how
lot
you're
of the
doing.
stuff says that it's overdue by like 4 years or a year and a half and stuff.
Then, well, I thought I'd gone through and changed those too. That's totally on me because my office worker didn't get to it.
And the homework is due at midnight, but it says on there that it's due at 5.
Right, we talked about that.
They
If you
panic
turn it
every
in-
time.
If you turn it in on paper, it's due at 5. If you turn it on Moodle, it's due before midnight. So that's why it has both of those times. Okay. I don't want people panicking. I want things to be clear. I have the 2 times because I want people to be reminded there are 2 different deadlines depending on how you turn it. Okay. Gravitational potential energy. I talked about this before, but we didn't go and do the calculation. We have potential energy is equal to minus the work done by a force, and work we learned was force times the distance parallel to it. So what's the equation for the force of gravity? Okay. What does the force of gravity depend on? Mass. And one other thing. It's the acceleration of gravity. mg, that's the force. And then we have the distance. Now here is, signs can be confusing. If I take this bowling ball and I am holding it, what direction is the force of gravity acting on this bowling ball?
Gravity's pulling it down.
Right.
You're pulling it
So if gravity is down and I lift this up, the direction of the force and the direction I moved it are opposites. And so that makes the force times the distance parallel negative because the distance was not the same as parallel, was what we call anti-parallel. But there's a minus sign in that equation as well. And so a minus times a minus makes a plus. So because the distance I forgot to put minus signs there. Distance up is opposite to FG, which is down. Then it turns out that this is equal to a positive mg, and I'm going to put h, d is equal to minus h. That is, well, so the gravitational potential energy is that equation here at the end. Gravitational potential energy is mass of an object multiplied by the acceleration of gravity multiplied by the elevation. So we're going to come back and use that as an example with the bowling ball swinging from this thing. Go past that. Kinetic energy. I guess I need to talk about kinetic energy before I talk about the work energy relation. Kinetic energy was energy in motion. And we get the equation for energy in motion with calculus, which clearly is not going to be done here. But kinetic energy, energy in motion, is 1/2 mass times speed squared. So the faster something moves, the more momentum it has, and the more kinetic energy. And the kinetic energy is proportional to the speed squared. And we saw this equation in lab yesterday. So before I even talk about that slide, I am going to do this. I think I have a picture with this coming up, but now is the time that I want to do this. I keep losing these. I have some little S things that are really easy and convenient, but if you lose them, you can't use them. Stressing out a little bit?
On the plus side, if it goes wrong, you can blame Union College and maybe get some tuition.
Get free tuition because I did a bloody chin?
Oh, it's coming towards you, not towards us.
Okay, no, it's not coming toward you.
I'm more panicked at this.
Okay, so what kind of energy does the bowling ball have right now?
Gravitational. That's secure.
Gravitational potential energy. What?
Is that like secured the concrete?
Yes.
Okay.
We can hang the entire class on there without stressing it.
Okay.
By the way, I was really happy that our pastor, I think it was our pastor here, used stress and strain correctly in the sermon. I think that's the one.
Well, they asked for details on how he did, so you could always go on there on the YouTube and write them.
Okay, so right now it has gravitational potential energy. When I let go, what's going to happen?
It's going to come back, but at a little bit more in like one step.
Okay, she says it's going to come back. She's going farther. I was going to get to that. She said momentum. It's going to start moving. Why is it going to start moving?
Gravity.
Because gravity's acting on it. But when that gravity's acting on it, it's doing work. And it's going to convert energy from potential into kinetic, the motion. Like
but we'll lose kinetic energy because it's not going to come at that all the way up due to gravity.
Air resistance and maybe some friction up there. So it's going to convert energy from potential into kinetic, so it's going to be moving. What would happen if I told Jessica to stand right here? It wouldn't feel very good. Why?
Force.
It would have kinetic energy, and when it hit her, it would apply a force. It would do work on her, because remember, work is force times distance. All of these things play together. So we have a lot of kinetic energy there, a lot of energy in motion, but then when it swings up on the other side, what's happening with energy?
It comes back.
You know, Dr. Webb, you should, next year, you should do this before that lab, just so kinetic energy is a little bit easier to understand in lab. Because I feel like this is a really good example of showing it and like understanding it.
Okay, I'll do that.
Tips and tricks.
Yeah.
Our fellow teachers.
From my fellow teachers. I took all these classes too in college. Except I didn't do student teaching, so I don't actually have teaching. And it would have inspired by now. Okay.
What? I'm ready for you to release that.
Yes. But I want to finish the topic. Once it's coming up, what's happening with energy? What's happening with energy when it's coming up?
When it's coming up, it's slowing down.
Which means kinetic is dropping, right? The 1/2 mc squared is going down. Where's the energy going?
Well, it's getting everywhere by gravity.
It's going into gravity. It's going back to gravitational potential energy. So this is just converting back and forth. Now, energy can't be created or destroyed. So if I let go, Jessica says it's not going to hit me. She's right. And Jessica's already given us the answer because she was ahead of the game. There was air resistance. It was moving air as it swung. As it was swinging. Let's use that form of speech. As it was swinging, it was moving air, and that was taking away energy from this because it was transferring energy into the air molecules to make it move. And so it didn't have quite as much energy. So when it came to a stop, when its kinetic energy was zero, its potential wasn't quite as high because it lost some energy to the air. So this is just transferring energy back and forth. The dangerous part of it, right, there's really in theory no danger here unless you, the teacher, are kind of alert and you can't stay vertical because you're like, leaning back here. And then if you lean forward after you let go, then it'll pound you. So that's a kind of fun demonstration. And Jessica said it was helping understand kinetic energy better, which is all the goal. So when you apply the brakes in your car, previously we talked about a force being applied and that causing an acceleration, right? Because Newton's second law, acceleration is net force over mass. We can now talk about a force being applied and that doing the work and taking away kinetic energy. You can actually solve the same problem two different ways. One way using energy and work, one way using Newton's second law. Often it's a lot easier to do it with the work energy method because force is a vector, it has direction. Acceleration is a vector, it has direction. Work and energy don't have directions. So it's often easier to solve these as work energy problems. I better move that just so it's not as much of a distraction. And
Oh my word.
What?
My phone said, you know how sometimes they pull up suggestions on iPhone now? Woo clap! It literally already has it ready.
I love your phone. I wish I
I've
was.
been out of it for like over a week.
Yes, but what it has learned is during this time period you're often using WooClap, and so it's suggesting, hey, why don't you use WooClap
at least
now?
it's WooClap and not online shopping, Dr. Webb. It knows that I'm paying attention.
So
working,
the online shopping shows up as the second activity.
working force, and what were the two other ones that you brought up?
Those were the two: work energy
And force.
and Newton's second law with forces.
Okay.
Now, the work energy theorem is a theorem about how the work and energy interrelate, and it says that the work, I have to put net here because you could have work adding energy and work taking away energy. The net work is equal to the change in kinetic energy. So if it's just the brakes doing work, then the work done by the brakes is equal to change in kinetic energy. If I drop a ball, let's say I drop a ball and there is atmosphere, because you know there's really air here.
Yeah.
As it's falling, gravity is doing work on it, right? But so is air resistance. And so the net work, you have to take both of those into account. Gravity would be doing a positive work, and air resistance would be doing a negative work. The net work, when you add those together, would be the change in kinetic energy, would tell us how much speed is picked up. Already introduced that equation. So how do we use this? Well, for our purposes, you need to be able to calculate the potential energy of an object. So let's just give a simple situation. Let us, oh boy.
Wait, will you go back?
These things here are supposed to be back there.
Like not even a whole second.
Go back to this.
Yep, we're good. That wasn't even a second. You're good.
Good, okay. Okay, so let's just do some basic things. A 5.0 kilogram mass is 1.5 meters above ground. What is its potential energy? So here is a 5 kilogram mass, and here it's being held about 1.5 meters above the ground. What's the potential energy of this mass?
I always forget what these letters stand for. Not those, but these that I wrote down.
Not those, these
Why
are-
it looks like this.
A
A 5 kilogram mass is 1.5 meters above. What is its potential?
What's the equation first?
Is it the
Half mass times speed squared.
That's kinetic.
its potential energy equals negative W, whatever that stands for? Does that work?
That was work, yes. You want to get to the end of that. That's the middle of the equation. But what do you have at the end of the line?
Force,
What was the force for gravity?
mass times the gravity
Yeah.
times the distance.
Yeah, the potential energy is mass times gravity times the elevation. That's the goal. So my mass is 5 kilograms. What is the acceleration of gravity? It's a number. You don't have to have it memorized.
Oh, the 9.8.
Yeah, 9.8 meters per second squared. So we can do this in our head. We'll stick with the textbook's number of 10, rounding it off. So we're going to have 5 kilograms times 10 meters per second squared. 5 times 10 is 50. Times that height of 1.5. 50 times 1.5 is 75.
Oh, you're really good at that. I'm over here like,
So it has 75. What are the,
See, I'm typing it into my phone, like, is that the correct number?
what are the units we get from that calculation?
half of 50.
Are you talking about like
Okay,
the
can you repeat the
joule
question?
thing?
Joules, that is correct. Go ahead.
I was gonna ask if you repeat the question.
Oh, the question was what are the units we get for that calculation of the potential energy? So it has 75 joules. Now if I let go, what's going to happen?
It's gonna fall.
Full floor
It's
gonna
going to
break.
fall.
And you might hurt your foot.
I'll keep it away from my foot. I'm not going to drop it because it would also hurt the floor. What would happen in terms of energy if I dropped it? It would lose potential energy, but it would transfer it into
Gravity.
Kinetic.
No.
Gravity.
Kinetic. It started as gravitational potential, but it would convert it to kinetic. So we have our calculations here. The first one we did was potential energy is mgh. So that was 5.0 kilograms times 10 meters per second squared times 1.5 meters. And we calculated that was 75 joules. And now the second question is, what will the speed be when it hits the ground?
0.
Just before it hits the ground.
How fast is it gonna get?
Yeah. That is a good answer, right? After it hits the ground and stops moving, it'll be at rest. So how do we calculate the speed? Before,
Kinetic energy.
yes, the kinetic energy. Before we would have said, well, it has acceleration of 10 meters per second squared, a distance of 1.5 meters, and we would have used our kinematic equation that relates distance and acceleration in time to find the time, and then we go and calculate the speed. But now we can say the work done by gravity is equal to minus the change in potential energy, which is going to be the final potential energy is 0 minus the initial potential energy of 75 joules. So we know the work is minus 75 joules. And then we have, let's see, actually, yeah. Minus change potential. Final one. Oh, minus a minus. Got to put the minus out front. The change potential energy is minus 75, and it's minus the change potential. So that means that my work is equal to 75 joules, but according to the work energy relation, that's the change in kinetic energy, which is equal to the kinetic energy final minus the initial kinetic energy, which it started at rest was 0. And then we use finally the equation that Jessica has been telling us, Kinetic energy final.
Half mass times speed squared.
That's right. And so now I just multiply both sides by 2, divide by m. I'm going to divide by m over 2. It's the same as multiplying by 2 and divide by m. And I have V final squared is equal to 2 times 75 joules divided by 5.0 kilograms. So 2 times 75, that's 150. 150 divided by 5 is 30. And the square root of 30?
36 is 6, so 30 would be 6.5-ish.
5.6-ish.
Yeah. My bad, I
You went wrong, yeah. It's somewhere between 5 and 6.
That's ugly and annoying.
Actually, it's maybe more like, no, I'm sorry that it's ugly and annoying. Because it's not a simple number, right?
I like it simple.
It's somewhere between 5 and 6. So we could find the speed that way. A second way of solving problems that before we could do with kinematics. Why is this easier? Well, here's one way this is easier. If I have the ball that was sliding down a ramp without friction, the distance it's traveled is much bigger. But all that matters for this is the height change. So it doesn't matter if it slides down a ramp without friction or if it falls straight down, it's going to have the same speed. So when you talk about something like a roller coaster with pretty minimal friction, it doesn't matter if the roller coaster falls straight down or if it comes down this nice, gentle slope. The speed you're going to have at the bottom is the same if you start from the same elevation from rest. Which is kind of cool to know. Roller coasters are actually a great example of physics.
Wait, but I feel like the one with the straight slope would be more expensive.
We tend to think that, but it's not right.
Really?
Yeah. They're the same, assuming friction is 0.
Yeah.
If friction is not 0, then the straight down is going to be quicker because you're probably going to have no friction there. Now here's another example. This is what's called a pile driver. You want to drive that post into the ground. There's 2 ways of doing it. One is you've got the post driver that you hold like this, and it's got a heavy thing. You lift it up and you go like that, over and over and over. It's a lot of work. Or there's a pile driver, and you would only use pile driver if you're putting in a really big post. You know, the kinds of things you use that for are stuff that are this small or smaller. And there you have a machine that raises a heavy weight and then drops it. Your goat herder, are you? Now, what would be wrong about this picture in real life?
It's not gonna land vertically on the stage.
Yeah, it's not going to land perfectly on the straight stake. It's going to bounce off. In real life, you would have something that is contained in the pile driver so it falls straight down and doesn't bounce around. But that's taken away so you can see the action. It starts at the top with potential energy. As it falls, that potential energy is converted to kinetic energy. And then when it hits, that kinetic energy does work. The net work equals the change in kinetic energy to drive the post into the ground. Simple machines. Let's once again remind ourselves, why are you in this class?
It's required.
You're absolutely forced.
You are absolutely forced. It's required.
Yeah.
Why are you absolutely forced?
Because we have to teach it at some point to the kids.
Okay?
Apparently.
You're going to have to see it, apparently. You have to teach it at some point to kids. Why are you going to teach it to kids?
I'm
sorry, it's like academics is required.
Because that's what we're teaching in
No, you
science.
probably will.
No,
It
it's
won't-
a very dumb.
Yeah, it won't be at this level, but you always need to understand more than what you're telling the kids.
Everyone's making me mess up my brain.
True story. A lady at my dad's church, when she found out I was a college professor, she was like, "Oh, teachers have it easy because they have the answer key.
No.
If you have to rely on the
God.
answer key, you're not a very good teacher because you don't know your topic." But she, I will not say bad things about her. Oh, isn't that a nice thing to not say you have things? So you have to take this class so you understand what science is about, so you can help your kids understand what science is about, because we use science to drive things. Like Vanessa was just using her phone, but that phone was developed by people who had to understand science at a very, very deep level. And so we have a lot of advances in society because through the scientific method, we have learned how to discover how nature works, how God designed our universe. So I actually want to review the scientific method before we go on, just to make sure, because you know on that first test, you're going to have a question, scientific method. What are you going to have to do with that scientific method question? Okay.
Find each part of it.
First, you have to give each step. So let's go through the first steps. What's the first step of the scientific method?
Observe something interesting.
Observe something interesting. The second step.
Create a hypothesis.
Create a hypothesis.
Based on scientific information.
Based on scientific information?
Based on something that you can prove, right? Like something like that.
Something that can be tested.
It has to
Yeah, something
have
that can be
predictions that are testable.
And
the last one's the one you skip because it's too obvious. It has to explain why the thing you observed happened.
oh yeah.
Right? You know that has to be there and you forget to list it. Now, Josie used the word prove. In science, we can't prove anything right. We can disprove things, we can prove them wrong, but we can't prove things right. What we can do is do experiments over and over and over until we're convinced. So we have the second step. What's the third step?
Well,
It actually,
to test your prediction of the hypothesis.
yes. So it does involve collecting data because you need to test your hypothesis prediction. You are not going back and checking to make sure your observation is correct. We presume that you correctly observed before you started. So your test is testing a prediction of something additional, something different that is predicted by your hypothesis. If you're correct, then what do?
Then you,
That's if
based
it
on the
predicts
outcome
correctly.
of the test, if it passes, you go back to step 3 and test a different prediction.
Right. And what if it doesn't pass? What if you
Then
disprove
you go
it?
back to 2 and test a different prediction.
Go back to 2 and you devise a better hypothesis because you have more knowledge now. So the scientific method is very pragmatic. You come up with a guess, a hypothesis, an educated guess, and then you test its prediction. If its prediction is wrong, you have more knowledge because you know, well, it's not that. And so you can make a better hypothesis. So the goal is that our hypotheses, that's the plural hypothesis, are constantly moving toward more correct answers. So what we understand today as scientific knowledge may not be the same as what we understand tomorrow, because we might run an experiment that shows, oh, this was wrong and we can improve it. Now, while I'm on this, you know, I'm a Christian, I'm a creationist, I believe that God created life on earth. And so creationists are often ridiculed by scientists, you know, you don't even believe in science if you don't believe in this. Christians, on the other hand, will ridicule scientists saying, well, I mean, you just have a hypothesis and you keep or theory and you keep changing that theory. Well, that is science. Science is changing theory. You don't get all upset when you have to change the theory. You're happy because you're learning something new. And so, just because I don't believe in evolutionary theory doesn't mean that I would say, oh, it's not science or it's lame because they had to change the belief. Because we do experiments, that's what happens in the scientific method. So it's supposed to happen. Okay, so simple machines was the topic that made me want to get back to this. Something you may observe. It's really hard for me to lift a refrigerator and put it in a moving truck. Well, nigh on impossible, right? But if we put a ramp on that moving truck, I can push the refrigerator up the ramp and get it into the truck. Is that something you guys have observed somewhere in your life? We call a device like that a simple machine. Well, you observe that, and the scientific mind says, why? Why am I able to do it with a ramp when I'm not able to do it without the ramp? And so then our next step is answering that why with a hypothesis. So give me a hypothesis, a reason I might be able to push the refrigerator into the moving truck if I have a ramp, but I can't just lift it and put it in.
The weight is distributed.
Unevenly.
Okay?
Stop.
That's a reasonable thing to do because you learned about the normal force. What direction is the normal force?
Down.
No. No,
The normal force
this is an important thing.
would be horizontal, pushing against it.
No.
The same direction it's going.
No.
Oh my goodness.
No, but this is important. We learn when we make mistakes, or we should learn when we make mistakes. The normal force is called the normal force because its direction is what we call normal in science. It's the direction coming out of the surface. So if the surface is on a slope, it's going to be like this coming out of the slope. Now to go with the question that Vanessa will be obviously correct on. What direction is the force of gravity? Because that's what you were thinking before.
Down.
Down, yes.
She's like, what word did I use?
The force of gravity is down. The normal force has a component that is, since it's pointing up at an angle, part of it is up. And part of it's horizontal. And so that part that is up is supporting the refrigerator. Not all of it, but it's supporting some of it. So my push only has to support what the normal force is not supporting. So based on our understanding of normal force, which is what you guys invoked, maybe unintentionally, but you said it's being supported by the ramp, then the force I have to apply is smaller. Now let's suppose that is our hypothesis. How would you test it?
By using other things than just your refrigerator and using different size ramps to see how easy or uneasy it is to push it.
Okay, the thing I would go with is the ramps. One that's really steep, one that's flatter, one that's flatter. If my hypothesis is correct, the flatter it is, the more vertical the normal force is, the more it's going to support the weight. And so it should be easier the flatter it gets. So if it's really long, then it's close to level. That's if the ramp's really long. And it should be really easy to push it up. And if it's shorter, it'll be harder. And so there's a test we can do, and since you guys are absolutely right, that's exactly what we would find, which you probably already knew from experience. So that's the scientific method cycle. So on the test, you're going to have to give the steps, and then I'm going to give you an observation. You're going to have to, so the observation will not be any example that we've had in class. The reason is I want you to actually be able to apply the scientific method idea and not just recite something you've heard. So you'll be given an observation, you'll have to say, observation is, and you just summarize what you were given because that was step one. Hypothesis is, and you have to write a plausible hypothesis based on scientific ideas. And then your test, you have to have a prediction that's different from your observation and how you would test that prediction. So you don't just say, I'm going to test this. You'd say, I'm going to have different ramps and see if it's easier with flatter and harder with the slope because my hypothesis predicts it's easier if it's flat. And then in the end, you'd say, if it's easier when it's flatter, then I'd have to go back and do a different experiment. You don't have to specify what the new one is, right? Because then you can go on forever. And if it turns out that it's just as hard when it's flat or steep, then I have to go back and change the hypothesis. That's really important to me that you can do that because when you're doing science with your fourth grader and you're talking about, well, my earthworms died, want that scientific idea to pop in your head, well, why would the earthworms have died? Maybe it's because
Your fourth grader ate them.
they
put too much water in the
That's what I was going to go with. So I say maybe it's too much water in the soil, and earthworms could drown because we know animals can drown. And then, we test. How would you test that? Well, can earthworms really drown? That would be. Don't kill animals in your tests, okay? Don't even torture them.
Yeah.
Okay, so a simple machine. The ramp is a simple machine. The purpose of the simple machine is to allow us to do work easier. Getting the refrigerator into the back of the truck, I have to have the same change in potential energy no matter how I do it. So the work done was the same in both cases. But when I used the ramp, the force necessary was smaller. Remember, work is force times distance, so if it's a smaller force, distance has to be bigger to get the same work. So with the simple machine, you are putting a smaller force on an object over a larger distance to make it happen. That's the whole purpose, the goal of the simple machine. Here's where I told you I had it later, the actual pendulum demonstration.
It's good that you did it when you did.
Well, good. So obviously, we're not going to do that one here. This is the ball demonstration that I did in lab yesterday, so we don't need to do that. By the way, that thing's been sitting there stretched out, storing potential energy since yesterday lab time. It never did. It's done. All right. Consider a system of a bow and arrow, and drawing the bow, we do work on system and give potential energy. When the bow string is released, most of the potential energy is transferred to the arrow as kinetic energy, and some as heat to the bow. We've already talked about that, right? Well, we didn't talk about the energy going to heat to the bow, because it's not very much. There's also a little energy that goes into the string, or not the string, but into air, making the air move, making sound. Here is the most basic of all simple machines, the lever. The lever is something that helps you lift a heavy object. So for my lever, I'm going to take a few masses over here and grab a meter stick. And the meter stick is going to be heavy. There are some terms here we should know. So this, the lever. The thing that I put it on is the fulcrum. Now, of course, your fulcrum, we always show a nice pointy fulcrum so it can't just sit there like mine is. Is it possible for me to put the 1,000 grams on one side and the 200 grams on the other side and make it balance?
No.
No, why not?
Oh, it is if you move the lever. You
Okay,
change.
so Jessica
You
says
change
it
where
is
the
a
lever is touching the fulcrum.
So if I change it where the lever is touching the fulcrum.
Other way, buddy. Other way. Oh, it is. Oh, yeah, it is. That makes me.
There.
Sorry.
It's okay.
Trying to trick it. Trying to see.
I would have went the other way too. I would have learned
That's
from my mistake.
Learning.
That's right.
Is all what
That's right.
science is about. Experimenting.
Is about experimenting. So here we have, so it's balanced. I have 1,000 grams here balancing 200 grams. And it's not just because that's a flat fulcrum. If I take it off, obviously it's no longer balanced. How is this working?
Because what's the word?
Because the small input force over a long distance
Because
equals
the
the
bigger.
output force over a short distance.
Jessica's been reading the screen.
But I'm right.
Of course you're right. So let's just think about this. If I go from here to here, how much did this go up? From here to here. Yeah, maybe half a centimeter. But this one over here, it moved more like 3.5 centimeters, 4 centimeters. So this one moved a lot bigger distance than this one did. And so the work done by this and the work done by this, when it's actually correctly balanced, is going to be the same. Now we're going to learn the word torque pretty soon, and we're going to talk about. Okay, that's enough of those. We'll talk about torques and how the torques play into it. But that is a simple machine example, and you can use it for all kinds of purposes, like in my backyard, there used to be a fence. It was just one of those, like, 3-inch square fence things, really ugly. So a student was renting from me, and I decided to go take it out. And so we're trying to pull out these posts, and some of them we can't get out. And so what do? We take a stick, and we just hook the post like here, and then we lift. So now our fulcrum was here at this end,
Yeah.
but this distance much different. So when I move this 1 foot, this moves up like 2 inches. Well, what that means is if we're going to do the same amount of work, my force is like 6 times bigger or smaller than that force. So I have 6 times more force, I can easily pull them out then. So it's something I used. 2 weeks ago, one of my students had, remember how icy it was? Yeah, he slid into a curb, busted up his front tire, so we had to change the tire. And those lug nuts were stuck. Well, how do you get it off if it's stuck?
Melted.
Melting it does, actually, you heat it up, things expand in it.
Yeah.
It comes off easier.
Heat it up.
That's absolutely right. But we didn't have that option.
So you use something bigger to push against it?
We used a longer wrench because that longer wrench gives us a bigger distance here, hence the amount of, in this case, torque is the right word. We were applying was bigger, and we were able to get them off. It still wasn't easy, but we got them off by using a simple machine. Very prevalent in life. The efficiency of a machine is the ratio of the work done to the energy you put in. In theory, we would like that to be 1. But in real life, nothing is ever perfect. You always have some friction and some losses. So the efficiency is the ratio of the work you actually got done divided by how much energy you had to put in. And final topic for today, I know this seems a little disjointed.
Oh, can you go back?
Energy sources. What is the most important energy source to life on Earth?
The sun.
The sun. Over 99% of all of the energy that we use on Earth derives from the sun. Which sounds silly, right? I mean, when you think about it, what do you use for your car?
Gas.
Gas. Where's that gas come from?
Fossil fuels.
From where?
Fossil fuels.
Fossil fuels. Where do the fossil fuels come from? Another option would have been from corn, by the way.
Well, they came from the sun, eventually.
Eventually came from the sun because those fossil fuels came from, if we're talking about petroleum, fossil fuels, they came from animals that died and they were in the right environment preserved and degrade over time and produce these oils. But those animals survive because of energy from the sun. Everything, all of our plants are the result of energy from the sun. The animals ate plants, or they ate other animals that ate plants. And so ultimately, those fossil fuels derive from the sun. So the sun is our important source of energy. Things that you may not think about. Things like, when it rains, why does it rain? How does the water get up there? The water gets up there because of the sun. The sun, and when we get to the geology section, we'll talk about the hydrologic cycle. But the sun heats water on the earth. That water, because it's heated, it becomes vapor, water vapor. And that hot water vapor goes up, condenses in clouds, and falls back down. And so if you're using something that's like a dam to produce your electricity, that energy ultimately came from the sun. We cannot create or destroy energy, but we can convert it from one type to another. Yes?
I was going to say preserved. Is that wrong?
Energy, conserved is the word that we use, not preserved. Energy is conserved. It can't be created or destroyed. But we can change it from one type to another. If you burn a fossil fuel, it's going to take a very, very long time for you to potentially replace it. And so that we consider a non-renewable energy source. Whereas if you burn ethanol, our fuel around here is 10% ethanol for most of the year. That ethanol is produced from corn, and we grow the corn every year. That's considered very renewable. Okay, have a happy Sabbath, a great weekend. I'll see you next week, which is another short week.
No lab.
That is correct.
Take